Welcome to another CO2 Monday in the Refrigeration Mentor podcast. I'm your host, Trevor Matthews. And once again, thank you so much for taking the time to come and hang out with us each week. I have a special guest here, Scott Martin, who is the Senior Director of Industry Relations for Hillphoenix, but he was the Director of Engineering and the Director of Sustainable Technology. He's been with them, I believe, over 28 years. And he's been in the industry forever. His granddad was in the industry. His dad was in the industry. We're going to dive into some of that, but I'm super excited to have him here because once again, Hillphoenix is one of the biggest manufacturers in North America, and globally they're growing. And I love seeing what they're doing with their CO2 applications. Scott, welcome to CO2 Monday. How you doing?
Yeah, I'm great. Thanks, Trevor. Thanks. Great to be here and great to keep spreading the word that you're doing so well.
Yeah, I appreciate that. We've seen each other when we were down in FMI, which was a great event. I really enjoyed that, getting to connect with you, getting to connect with a lot of the other people who really believe in naturals, and seeing how the evolution and the technology is starting to grow, because we went from these, as we're going to talk about, these basic systems now to these more advanced systems where we can put them anywhere in the world with better efficiencies than we did 10 years ago, which is great to see, right?
Yeah, it's pretty exciting. Awesome stuff. That was one of the sessions that I had, was dispelling or debunking the myths of CO2. There's a lot of people, Trevor, as you will know, that are not fans of CO2 and will say and do anything to keep CO2 from catching on. And, our job was to try to tell the truth. I used to be in that same camp. I was afraid of the pressures and thought no way, no how, until, we really started diving in and playing with CO2 ourselves and got familiar with the technology. And then, it was a big 180 reversal for me.
Yeah, and that's what it takes. It takes a little bit of just understanding, seeing it to believe it, because once again, it is evolving the whole time, but you need the right people to talk to you about it and show you, it's just like refrigeration. When I first went into my first rack room and seen all the controls, seen all the compressors, I'm like, I'm overwhelmed. And it's the same thing with CO2. It's like, yes, it's higher pressures, but there's lots of things that you just need to understand about it. And after that, it gets so much easier.
Yeah, so what this system was, we had plate heat exchangers connected to a rack, and, the refrigerant was not important, what was up on the top side there. But all of this, the CO2 was the blue piping, if you will. So the liquid vapor separator, the vapor would rise to the top because this plate heat exchanger is cold, and that vapor CO2 would condense inside, fall to the bottom. We would pump that out into the store. It was really simple control too, no expansion valves, on off control, the liquid line solenoid valve. It was, if your walk-in box or case needed cooling, you just open the valve and cold CO2 would flow through. Then this is the challenge, right? It's a mixture of a two-phase flow, some amount of liquid, some amount of vapor, depending on the load on the evaporator. So you bring that back to the liquid vapor separator, the liquid would fall back to the bottom, and the vapor would separate out at the top, and that whole cycle would repeat itself. And this is a good system for low or medium, and we've built both, and we still build these systems for some customers that just really like the performance of it. And the
low refrigerant charge, right? The low refrigerant charge.
Yeah, you're cutting your refrigerant charge by at least 50%, maybe even a little bit more, depending on what you do, how close your air-cooled condenser is to the rack, and, all of that. If everything's close coupled, you can cut that charge even further.
Yeah. And I think we'll still see, though, I know for sure we're going to see more of this design down the road, because with all these different regulations reducing GWP, there's not every store is going to be able to go transcritical. Just the design, the electric may be coming in, the disruption of the store. So I think going CO2 pump systems, we're going to see a lot more of these, honestly, I believe anyway. And so in that plate heat exchanger, we call that thermal siphon effect. I'm pretty sure that's what they call it. Similar, if those of you listening that's in industrial, they talk about thermal siphon effect. You see that a lot in the industrial side. It's the same thing happening here, just like Scott explained. What are some of the things that you guys learned along the way? Because you perfected, this is almost 20 years you've been designing this, and you've been changing, you've been evolving it for over 20 years for sure. Like newer designs, newer pumps, I'm sure, newer VFDs, newer plate heat exchangers that are more efficient. Over time, things get more efficient. What are some of the maybe one or two of the learning things from this? I know you said insulation was a big one, going out to the stores or ice, but what are some of maybe the design changes maybe since 2006 to 2023?
Yeah, just more efficient ways to make it more compact. You know, how you pipe that liquid vapor separator and having a tangential inlet coming out of the plate heat exchanger to go in. So you could drop. It's important that that plate heat exchanger is up above, but you know how you pipe that liquid outlet. You can lower that and have a tangential inlet to the separator. What's also a change was the expansion valve and the controls there, making sure that you have good interaction between the rack and the expansion valve, just like we do today on booster systems. So if there's any problem on the rack, that you can close a liquid line solenoid valve and not flood that rack out during startup. Yeah, so a lot of lessons learned since 2006 when we deployed the first one. You know, Trevor, we put this thing in our lab and ran it for a couple of years to understand it and, you know, the best way to apply liquid CO2 in our lab.
Yeah. And that's important to do. It's still going to be different when it gets out to the field, because different contractors, different technicians install. Sometimes things don't go as planned with whoever the architect of the building is, so things get changed, as you know. But the big thing about this one, when I do a lot of my trainings, everything on the primary side is exactly what you work on in supermarket today. Everything.
Yeah, exactly.
You know, then when you get down to the CO2 side, you got a pump, and it's just pumping it out. One thing that though I did learn is, because I've worked at one or two stores that had one of these. I think are they called Second Nature, these ones? I'm pretty sure they are, but
yeah, it was under our Second Nature. Our marketing team, you know, developed that Second Nature umbrella. So all of our technologies that limited the refrigerant charge or used natural refrigerants were Second Nature products.
Yeah, one thing that I learned though, like on these ones compared to doing HFC or synthetic refrigerants, and with synthetics, you have a smaller liquid than your suction. These ones here, you could have two the same size, your liquid and your suction. Yeah. Both be 5
times the supply and return will be both 3/8, you know, because that's one thing that people don't know about CO2 is the liquid line and suction line, if it's DX, are at least one size smaller than traditional systems. So, but yeah, if it's a liquid supply and return, you can have some really small pipes. It's a way to save on the installation, right? You have a smaller copper, and the hangers are smaller, and the insulation is smaller. So it's a good bit of savings there. And not to mention that the CO2 itself is less expensive than the refrigerant.
Yeah. And so from there, you designed the secondary. So this is a secondary pump system. I'm assuming that you evolved from that into more of like a Cascade design. Oh.
Yeah, here you go. There's a Cascade system for you. It's a very similar receiver, plate heat exchangers, but now the low temp was special CO2 compressors. You know, Bitzer recips or Copeland scrolls are the primary ones that we started using here in this application, and discharge up through a desuperheater, depending on the application and location of the equipment. And then the hot gas went into the top of the plate heat exchanger and came out as liquid CO2, and it went out through. Now, though, we introduced the use of electronic expansion valves. So no more liquid line solenoid because we would expand that liquid. Of course, you don't want to compress that liquid back in the compressor. And we warmed it up a little bit coming out of the evaporator through a suction liquid heat exchanger before we entered back into the compressor. The cool thing about this system is 100% of the refrigerant on the low temp side was CO2. So now you've got, a CO2 global warming of 1 for the whole low temp system. So big savings on your carbon footprint going to a Cascade system here.
Yeah. So let's talk about one component there, this CO2 superheater. I'm sure that was something that wasn't planned right off the bat. That was something that may evolved after doing tests, because I've seen it in many booster applications where they added a superheater because they were having cracked plate heat exchanger. Have you experienced stuff like that, or is that how it came about, or did you guys think about this before you designed something like this? Because this is a new design, right?
Yeah, but we did, because of all the lab experience and lab testing, we knew that we had to have that superheater in there to lower that temperature going into that plate. And that's what you're talking about, is that inlet, hot gas temperature to the other side, and it kind of causing a stress fracture in the plate there and causing a leak. But yeah, superheater and the control of it is critical too, because you can cause yourself some operational problems if you start and stop that fan at the wrong place.
Okay. And so, I'm assuming that if you stop it, all the compressors are running, there's a high load on it, you're sending a lot higher temperatures up to those plate heat exchangers. If you're not really superheating, you're just going through a coil, there might be a little bit happening, but if you got no fan happening, you're still shooting that hot gas into that cold plate. Is that?
Yeah. And there's some cool things you can do too with, if you've got a chill water system somewhere in some big industrial process facility, a lot of times they'll have a lot of chill water available. So we've used that chill water as the superheater. Good way to use, what you have on hand, so to speak.
Yeah, and
this was a great learning experience. I think it was 2008 when we put in the first one of these.
Wow.
In some supermarket applications. And then we started looking at, what do you do? You've got this low temp or medium temp liquid overfeed system, which it's more efficient than a glycol system, right? Like the pump energy for CO2 is like 10 times less than the pump energy for glycol. So it's really small pump energy. Now the CO2 pumps are expensive, much more expensive than a glycol pump. But so we were building both of these systems, and if you look, there's redundant components in the tank, the plate heat exchangers. So then we started combining those two. We kind of just smashed them together into one, and we would build these combination systems. So everything in the store would be CO2. You could use the medium temp CO2 to cool the medium temp cases, and the low temp was all Cascade. And then you had just one top side refrigerant. Big gas savings here. You could cut your total refrigerant by 75% by doing this type of system, eliminating all the HFCs from the low temp and cutting the medium temp at least in half.
Yeah, and that's very cool development, and I'm sure it took a long time for you guys to figure out how is it going to work. You know what I mean? I'm sure it was fun at the time learning these new things and developing this, because it would have been super cool for me to understand that, and just seeing all the trials and tribulations along the way, because it's not easy to do this. Like, you're taking technology that haven't even really evolved, 2006, 2008. And I don't know what year was this?
This was like 2010. There for a while, every 2 years, we had a new technology that we were deploying.
Yeah. So you're taking these they're all still new technology. It's 4 years in refrigeration is still new technology. It's not like the iPhones today where every 6 months there's a new one. It's refrigeration. So you're taking these, putting them together, you're learning a lot from them. And then this is where, if that's 2010, this is where I'm sure the beginnings of talking about the booster system, their transcritical boosters. I'm sure you talked about it earlier, but that's your next evolution, I'm assuming.
Yeah, about that time we were planning, it was already being deployed in Europe, and we were watching what was happening there. And we had ordered all the parts to build our own booster system in 2010. Wow. And then we connected with Advancer, and we went to their facility, they came to ours, and it was just a perfect partnership because, there was no conflict on their side. And if we bought them, and there was none on our side. So that's what happened. We purchased Advancer, and they built that booster system for us for our lab that we installed in our test facility, which, by the way, we still have that rack, and we use it to test different components on today.
Wow. And so that's running over 13 years, 14 years now.
Oh, yeah. So we rebuilt it, reconfigured it for hot gas defrost, and, just a lot of different things, testing oil separator designs and oil separator efficiencies. A lot of learnings from that first test rack from Advancer. There's the simple 100% CO2, pretty simple design. You got those two valves, the high pressure valve and the gas bypass valve, that are unique to a CO2 booster system. But, they're not a lot different than the A9 valve receiver pressurization valve, or the, A81 valve from Parker that'll flood the condenser to cut the surface area in the condenser to keep your head pressure up in the wintertime. Yep. So it's not a lot different than that. And what's cool about this is, Trevor, is just everything on this rack is totally electronic. And so all these valves they're all electronically controlled. You get a great program in there, and this rack just runs. It's like, I equate it to the automotive industry. Way back whenever I was a kid, everybody, had muscle cars and with carbureted engines on them, and you had to adjust the valves, adjust the carburetor. You had to really know what you were doing to be a mechanic. And we've transformed to today. We have electronic ignition, and everything's controlled by the computer, and we get way better fuel efficiency, power, everything. The reliability of modern automobiles versus the 60s and 70s model automobile that are really great if you know how to work on them. Yeah. But there's a lot of people that don't. And so, our industry is going through this transformation like the automotive industry did in the 70s.
Yeah, it's unfortunate it took this long to get to this point, but it's a learning experience for our industry. We are definitely way behind most industries when you look at it. When we go and look at all the different, just like your example there, we are definitely behind, but which is good for us because we're going to start seeing this evolution. And you've been seeing it for 2 decades. You've been watching it continue to evolve. Let's go back just to a little about the beginnings, because I know when you first started working with CO2, it must have been like, this is different, higher pressures. I'm sure you guys learning about it in the lab, a cylinder at room temperatures, 816 PSI versus what you were working on 404 or whatever, a couple 100 pounds. Let's talk about that transition as you, in your beginnings to where you get up to this point where you're working with Advancer and you're designing system at this point. What was your thoughts when you first started seeing CO2?
Yeah, so same as everybody else, I'm sure. Everybody, oh, the pressures are high, and they are higher. And I wish I probably should have put up a diagram here that had the pressures on this. You got 200 pounds of suction pressure on low temp, 400 pounds of medium temp suction pressure, and 500, 600 pounds of liquid pressure. But the differential pressure is like the same. It's just your base point just comes up. So, I mean, the pressure drop across the expansion valves and across the compressor, the pressure, even in some applications, is a little less than some HFCs. So you just have to get it in your head. But, I'll never forget my first trip to Europe in, I don't know, the early 2000s, and going into a motor room. And I was expecting these big, loud machines and vibration, the pressure. And I will walk in there and I'm like, well, this machine room's like any 404 machine room that we're building at home. And I was almost like, are you sure this is a CO2 rack? And, I went to all different manufacturers. A great guy took me on a tour around Denmark, actually. I'd never heard of Advancer at this time, but he showed me an Advancer rack and showed me all these other racks built by various manufacturers. And I was just blown away that they were so prevalent. And the pressures were, yeah, they were higher, but you had to look at the gauge, Trevor, to see that the pressure was higher. You intuitively didn't understand that the rack was running at this high pressure. And it was not at all. That was like the big aha moment for me, going into a machine room and hearing the compressors run and expecting, all the vibration that wasn't there.
Yeah. And one of the biggest things that I do, because we just talked about it, in a cylinder, it's 816 PSI. It could be running at 1450 PSI or 100 bar at some points, in the middle of the summer. But I talk to technician, I say, you use nitrogen? You ever use nitrogen? Oh yeah, I use nitrogen. You carry it on your shoulder and walk into a store. Yeah, I've done that thousands of times. But it's 2,000 pounds of nitrogen on your shoulder and only 816 pounds of CO2. Usually you're not carrying those because they're big, heavy bottles. You'd be a big, strong guy. Maybe I could, but but it's you just got to I try to put it into context of what they're doing now. Like that nitrogen is way higher pressure, and you're just driving around, you throw it in the back of your van, driving around, like, got to tie that stuff up.
Not even thinking about it, right?
Not even thinking about it. But you work with that pressure every day, these technicians out there. So it is a little different. It isn't a system that is running, but I've worked and seen so many of your guys' systems, so many of other manufacturers' systems, the larger ones, and you guys are all building it to safety. All the codes, all the stuff, there's codes to this. You can't just throw anything together and sell it. There's a lot of codes and standards that you got to follow. UL here, and then in Europe, you get the PED. So all of these things, when you guys build a piece of equipment, there's a lot of safety factors. Want to talk about that evolution for you guys when you got into the transcritical? Because once again, it was still very new to you guys in 2010, 2011, 2012, versus the 10 years earlier you went to Europe and seen this stuff, right?
Yeah, and it took us, a year. I was looking it up just to refresh my memory. It took a year after we acquired Advancer to get the UL certification for North America. So it was like no easy, quick process, which some ways is kind of frustrating because Advancer and other people are building thousands of these CO2 systems in Europe, and they're completely safe. But, when we come here, we can't build it because we don't have UL approval. When we worked hard and, using all UL recognized or approved components in the system, and got that listing about a year later. So yeah, since 2011, we've been building UL approved CO2 booster systems.
Yeah. And that's amazing. So this summer I was with my good friend, Eric Holland from Advancer, and he says he worked with you quite a lot back in the early days when you guys started to build these. You want to talk about that learning experience you guys had? He said he spent a couple of months in
Yeah. He, the controls, Eric was focused on the controls. And whenever he came over and worked with us in our lab, we had Danfoss was kind of the only North American manufacturer that knew or could build CO2 equipment or control it. And so we had to work with Microthermo next, because a lot of Canadian customers, as you know, use Microthermo-based controls, and then Emerson. And so, yeah, that was his first assignment, if you will, was to get all these other control vendors up to speed where we could properly control a CO2 booster system. North American platform controls.
That's a project taking control manufacturers that don't do CO2 and try to integrate that. I can't imagine how that was and how that went, but it evolved and it happened and it continues to grow, because he was talking about different stories on how the different platforms worked and the way they had to integrate stuff. And I can just imagine like the things that they've learned along the way to develop those controls, and which we continue to see evolve. Like the E3 just recently came out, going to reduce the amount of those flex combiners that used to have to be used, right? So, which is good.
You took the words right out of my mouth. Everything in the E2 was all flex combiners, and then that was Eric pulling his hair out, writing all those flex combiners, and repeating that from job to job. And then, the E3 coming out made things much easier.
Yeah, no, excellent. So back in the early, 2010, 2011, 2012, 2013, you started designing these. So you have a product now. When was the first one you actually launched, like your first transcritical booster system in North America?
Oh, wow. I didn't look that up, but the first systems were actually built in Denmark by Advancer and shipped over here. And we put on some controls and, everything to make the control panel UL. So it was probably 11 or 12 that were the first systems that went in. And then we started building them in probably 2013.
Wow.
So 10 years now here in our factory here in Conyers.
Yeah, that's amazing. So we're over 10 years, transcritical booster systems here. And I know for sure, like even there's some in Quebec, they had them in the earlier here. But the thing is that I talk to people today. It's like, man, I never heard of CO2. This is new to the supermarket. How long have you been in the supermarket game? 10 years? Well, it's been over 10 years that we have transcritical booster systems out there. So it's just trying to get this knowledge out to evolve it, because it's not only in supermarkets now. We see it in ice arenas. We see it in heat pumps. We see it in industrial applications. So transcritical systems are out there, and there's a lot of them. There's a lot.
You mentioned a great application is ice rinks is for CO2. And I'm not much of an ice skater, but they say that, if you're playing hockey on CO2 ice, is much better than, the old ice, because the CO2 continues to boil under the ice and it makes the surface more even, where you can get cold or warm spots in the ice as a glycol goes under the ice and absorbs heat. It can warm up. And so it's kind of cool technology, different variations of it, right?
Yeah. And it continues to evolve. This is the big thing too, because back in the early days, so 10 years ago when you started developing, these were probably pretty basic booster systems. You were putting them in the colder climates. You were putting them in Canada or northern states where it's cooler out. How did it start to evolve into more of these high ambient strategies that we see today? Adiabatic, mechanical subcoolant, injectors, so on and so forth. When did you guys start to evolve that to get them down into warmer climates?
Yeah, we did a store here in Atlanta, and with an adiabatic gas cooler, we started working with BAC, developing their adiabatic gas cooler, and we put the first one here in Atlanta. That was pretty cool. Getting a CO2 store here in Metro Atlanta and that super hot Atlanta climate, and since then they're all the way down in Mexico and Central and South America. There's a lot of technologies that have allowed CO2. The CO2 equator, really kind of got all blown out of proportion, and that CO2 was not suitable below the Mason-Dixon line here in the States, and it really was more of an energy line. If you go in the southern climates, probably a Cascade system is more suited from an energy standpoint. It didn't mean that it wouldn't work, but that's kind of like, the people like we talked about at the beginning here that were not fans of CO2. That's one thing they said, oh, well, you don't want to put a CO2 system in Florida or Georgia. It's too hot there. Texas, it's too hot. And yet we got them all over Texas, Florida, Georgia now.
Yeah. I've heard lots of people say it won't work in high AMIs. What do you mean it won't work? Yeah. Refrigeration works everywhere. No, it won't work.
It has to, right? You can't have refrigeration turning off.
Yeah, exactly. So, and it's all about the design and the install and the commissioning. It does take a while. It's new. It's new. When something new comes out, you got to learn it. And it does take time. But honestly, like I've trained thousands of people on CO2. The guys that are working on stores all the time, CO2 stores, they way rather work on the CO2 stores now than the HFC stores. They don't want to go to the HFC stores. They want to go and work at the CO2 stores because they can see what everything's going on. They can troubleshoot from the trend graphs. They can go in and they can manipulate things if they need to test, to do easier testing than before. So it's quite an evolution.
Yeah, because everything's electronic, right? You can go, before you ever get in your truck to go to the store, you can dial up the store from your desk to kind of see what's going on there, so that if you're dispatching someone to the store, you can tell them, hey, check this and that. This is what's going on with what I'm seeing on the screen here, and go check it out. So there's a lot of pre-diagnostics that can take place, because everything is, that's one of the things that people do like about it. You have your laptop or your screen on the controller there. You don't need to run and grab your gauges and put them on the rack, because all the transducers are already there for you, and you can see the pressures without having to go through the kind of what our normal process,
Yeah. And that's one thing that I love about it. And this is how technicians that are even newer at CO2, they know supermarket. You need a background. You need to know that you need to take training. First of all, you need to take CO2 training. You need to take supermarket training if you haven't, but you need that safety factor training, and you should get that from your company, or you come to Refrigeration Mentor and get trained, or get from the manufacturer. It doesn't matter. You need that training. But after that, you can have someone help you troubleshoot a system, without having, just like you say, someone running around, okay, I got to go on the roof and put on some gauges. Okay, I got to go down to the case, put some gauges on. I got to put some gauges on the rack. Now you can see it as a full picture, which is really cool.
It's the whole system, right?
Yeah.
You can see the whole system in operation. One thing, Trevor, I jumped ahead. I was going to say something else about this myth about pressures, right? We all have played paintball, right? And the original paintball guns were CO2 cylinders. Yep. And in 75, 80 degrees, that cylinder can be 900 PSI. And you've got that cylinder in that paintball gun, like under your arm, and you're running, and jumping and playing with your kids. And nobody thinks anything about the safety of that paintball gun. Or if you're a scuba diver like me, the cylinder that you strap to your back with that valve right behind your head, that cylinder's at 2,000, 2,500, or even 3,000 PSI. Yeah. Way higher than the system we're talking about. So we got to get people, and thanks for all the training that you're doing. We have our own training program that Rusty Walker does a great job of training.
Awesome.
30, 40,000 technicians, but it's not enough, right? We need other people like yourself out trying to dispel the myths that, CO2 won't work in hot climates, the pressures are too high, it's an energy pig, all of them. You hear those myths all the time. So thanks for doing that and, helping kind of like calm down everybody that this is not something that's brand new. Like you said, we've been doing it for 10 years, but that's still pretty new in North America.
Yeah.
Europe, they're way further down the road. We get excited. We say we built 1,500 systems in North America, and Advancer's like got 16,000 or something, and they don't even have the largest number. So it's crazy the difference in Europe versus here.
Yeah, they're putting more CO2 racks out a year than we even have in North America. Like that's the manufacturers there. So it's going to continue to evolve, you know what I mean? Which is really cool. And it's going to continue to evolve. And I see the energy numbers starting to come down more and more every year. These newer systems and newer technologies, the cost of using CO2 is getting closer and closer to HFC or HFOs or these new A2Ls, whatever. So, which is good, and it's going to continue to evolve like that. What is the next step for transcritical booster system for Hillphoenix Advancer?
Yeah, so expanding the application, right? People are toying with bigger and bigger systems going in industrial application because, we talked about ammonia earlier, and we toyed around with building ammonia systems on the top side. We actually have one of those combination systems at a U.S. military base in San Antonio, Texas, that uses ammonia modules to condense the CO2. And it's really efficient and works great. But it was just too expensive, Trevor, using ammonia. So, ammonia is a great refrigerant, but the components are very expensive. And now we're seeing the CO2 technologies pushing up into the ammonia space. So larger and larger systems to compete with smaller ammonia installations. So that's one. Expanding the application. And we talked about ice rinks. There's others. We're not toying with it ourselves, but data cooling centers, it's a great refrigerant for that application. And heating, with all of the decarbonization strategies that are going around to eliminate the use of natural gas. And, CO2 is a great source of heat. And because the discharge gas temperatures are much hotter, it's hotter even than the old R22 days for guys that remember the discharge gas temperatures of a low temp R22 rack was pretty stinking hot.
Yeah. My fan's not working. My demand cooling's not working. What's going on? How come my eyesight glass is brown and black?
Yeah. So now CO2 is built for that temperature, right? And you can use that super hot gas to heat the store. Yeah. And so that's another reason why it's so beneficial in areas. And that's even coming further south, right? That you can just heat the whole store with your refrigeration system.
Yeah, and that's amazing, and that's here already, and it's going to continue to evolve that way because you can get so much heat over the last since refrigeration started. We're just rejecting it to the atmosphere, reuse it if we can reuse it as much as possible, and it's going to make your system more efficient. And this is what comes back to the design. That's what I think. One of the most important is like who you're working with, your end user, the contractor, the consultant, if there's a consultant, and the manufacturer. You got to all be in conversation to figure out exactly what is going to be the best result for that end user, right? And I think that's the biggest thing. And as long as everyone understands what's going on, it makes it for such a great project. I got one last question because we're starting to get close on time here. But when I was in Europe, I love the guys at Advancer. I see a lot of ejectors under systems, and all the manufacturers over there that I see more and more systems have either multi ejectors, they get single ejectors. How are you guys doing with that? I know for sure you guys been testing it. What's that evolution coming along, and how's that looking?
Yeah, so we've done some installations of high pressure injectors. This running in parallel with the gas high pressure valve. We were a little nervous because it adds complexity, and we need to get our technician level up where they understand basic CO2. It works well. It saves energy. It's just the added complexity, added cost of that. There are other technologies that you're going to see soon on some standard products from Hillphoenix that are low pressure ejectors, ways to save energy, and be looking for that as a standard product offering release coming soon. But yeah, we're always looking for opportunities to save energy, and there's a lot of different new products out there that we're evaluating and testing in our labs, and even in some field trials, and hopefully we'll be able to talk more about those sooner.
Yeah, no, I'm excited about it because I'm seeing newer strategies come out from different companies that are just, wow, this is pretty cool design. So I'm excited to see some of that because I know there's a lot of people and different manufacturers working towards building new components that are making CO2 more efficient, which is exciting.
Well, it's not just the efficiency in the energy used, but it's efficiency and price. When you have a big market share, there's new compressor manufacturers who spent the money to go get UL on their compressors, and you're going to see them in the United States and Canada more and more. So it's kind of been a smaller market share for a few select components. You get different people making high pressure valves, and thank goodness for the leaders that pioneered that.
Oh yeah, Dan.
For me, now there's other people that can build that, and give everybody some competition helps everyone.
Oh, I even talked with Dan Foss, a lot of great friends there. They pioneered most of the stuff that I know of CO2, and they're like, this is good for us. We're going to make bigger and better and stuff. They're working hard. Like I see lots of stuff in the background, what they're doing. They're coming out with some cool stuff. So even these new guys that are building the stuff that they have already designed, developed, it's good. And this is going to help everyone because it's going to reduce some of the pricing, right? And PX valves, the very first one, I'm sure was $10,000 for the very first one, and you can go buy them for $40 or $50 at the wholesaler now. So that's the evolution. And we're going to see more and more of this, which is pretty cool.
Well, what's really funny about what you just said is buying it at the wholesaler. Way long time, 10 years ago, we had our own safety stock with that was a 24-hour dispatch, because we would have to, you couldn't have a store go down. So we would all carry a phone over the weekend. I would carry the phone. If it rang, we had to ship parts out. So see, just a few years later, now wholesalers are carrying the parts. So this is the progression of the rollout of technology.
Yeah. I'm super excited about it. Scott, I want to thank you so much for taking the time to share some of this history with me. And I know I'm going to learn a lot more from you and your team. I appreciate you taking this time, and I want to have you again on the show at some point.
Yeah, I'd be happy to do that. And we appreciate the opportunity. It's exciting. People like yourself that are, stoked about CO2 technologies and want to teach people and, calm those fears. And however we can help do that, we want to participate. So thank you for all the work that you're doing, helping technicians become familiar with this technology.
Thank you, Scott. And I want to thank everyone for taking the time today to come and hang out here. Once again, share this with other people, share the YouTube, the podcast with people so they can find out about CO2. We've got over 80 CO2 videos on the Refrigeration Mentor YouTube channel, plus on the podcast. And this is what it's all about, sharing this knowledge. There was quite a few great tips that I got from Scott today. I look forward to seeing you at the next CO2 Monday and Refrigeration Mentor podcast. Thanks, everyone. See you later.